Morning, everyone. Welcome to the 2023 AIAA von Kármán Lecture in Astronautics. Very happy that you could join us this morning. My name is George Lasiert. I'm the awards chair for the von Kármán Lectureship in Astronautics. This lecture is named in honor of Theodore von Kármán, a world-famous authority on aerospace sciences. The lectureship recognizes an individual who has performed notably and distinguished themselves technically in the field of astronautics. It is my distinct pleasure this morning to introduce you to the recipient of the 2023 von Kármán Lectureship in Astronautics, Joseph Majdalani. Professor Majdalani has been a pioneering researcher in aerodynamics and rocket propulsion for more than 30 years. He is a prolific scholar and exemplary mentor who has been invited to present more than 97 seminars and plenary talks worldwide. He has over 300 publications and 18,000 citations of his work. Professor Majdalani is active in AIAA through technical committees and regional activities, and he's received numerous AIAA awards. He is an AIAA Associate Fellow. As a well-recognized authority in the field, Professor Majdalani recently co-authored a textbook on the subject of viscous boundary layers. Along the way, he developed several new formulations based on von Kármán's approach. These lead to an essentially exact solution to the celebrated Blasius equation, whose analytical treatment had remained intractable for over 100 years. Professor Majdalani's technical research focuses on advancing acoustic instability and rotating flow theories in the context of solid, liquid, and hybrid rocket engines, especially those driven by tangential injection. He's developed new effective methodologies that have been successfully applied to various rocket systems, including the class of cyclonic vortex engines pioneered by Orbitect and Sierra Nevada Space. Professor Majdalani's lecture today celebrates the centennial of the momentum integral approach, one of the most significant theoretical contributions of Theodore von Kármán, and taught widely today in the field of aerodynamics. He will discuss the broad impact of this approach, which was introduced in 1921 and often used in conjunction with Polhausen's polynomial approximations. Please note that after the lecture, we'll have a Q&A session. Given the nature of the audience, we'll be able to take questions directly to the speaker, or if you like, you may use the QR code listed on the screen or in the bookmarks on the table. Now I'm pleased to invite to the stage Professor Majdalani for his lecture. Joe? The lecture is titled Celebrating a Century of Kármán's Momentum Integral and Space-Reductive Approaches, Applications to Rocketry and Beyond. Over to you.
Thank you, Dr. Lasiert, for this very nice introduction. I'm absolutely thrilled to be here today to share with you some of my thoughts on first von Kármán and his legacy, some of the work that he has done and its relevance today, and also some of the recent findings we've had in modeling cyclonic rocket engines. So there's quite a bit of material that I'd like to go over with you today, starting with the man of the hour, Theodore von Kármán. Everyone knows Theodore von Kármán or has heard of him. To me, he's a personal hero. Even at an early stage, his parents recognized that he was a prodigy in mathematics. For that reason, they encouraged him to move to Göttingen later on to study under Prandtl. After getting his degree from the University of Göttingen, he moved to TU Aachen along with his colleague Karl Polhausen. We're going to talk about both of them today. And there he developed several theories that have become very relevant in the academic community. After that, specifically around 1930, he was invited to move to Pasadena, California, where he ended up directing and promoting the Guggenheim Aeronautical Lab. 2 years later, and something that most of us perhaps do not know about, he ended up founding or creating the Institute for Aeronautical Sciences, which later on would become one of the arms of AIAA, the other arm being the American Rocket Society. So in a sense, most of us are connected to von Kármán through AIAA in that manner. Now, of course, he was absolutely instrumental in establishing several institutes and advisory committees and boards, including, of course, the Jet Propulsion Lab, including co-founding Aerojet. At the time, it was Aerojet General, and also the Institute for Fluid Dynamics in Belgium, now named after him. He also helped establish several advisory councils within the Air Force, working with Hap Arnold, General Hap Arnold. They founded the Scientific Advisory Board and also NATO's AGARD committee that is still active today. And finally, he was recipient of several awards, the most important of which was the first National Medal of Science conferred upon him by JFK himself. Now, of course, his most enduring legacy could be found perhaps in the people that he inspired, and these include big names such as Frank Marble, Dr. Bill Sears, Martin Summerfield, who later went to Princeton, ended up with 50 doctoral students himself, and so on. But before we get into that, I wanted to talk a bit about his impressive legacy. So von Kármán was a student of Professor Ludwig Prandtl. At the time, Professor Prandtl was the leader of the world of aerodynamics in Europe and the world. He had many well-recognized colleagues, such as Karl Polhausen, Hemans, and many others, Blasius, for example. We're going to talk about them a bit today. And Prandtl himself was a student of Vöpel. Vöpel was a student of the eminent mathematician Felix Klein, and the line goes back to Dirichlet, Joseph Fourier, Joseph-Louis Lagrange, and Leonhard Euler, perhaps the most distinguished names in mathematics, if we leave out perhaps Ramanujan. So really an incredible legacy. And when von Kármán passed away, one of his students, who was very well known, had worked both in industry and academia, Dr. Bill Sears, had become a noted faculty member at Cornell University, was asked to write his in memoriam. And instead of his writing an in memoriam, he wrote some recollections of Theodore von Kármán. And this being a lecture, that would be the first recommended reading I would give the audience and our audience online. It's a phenomenal read. Every person who's read that has told me they enjoyed reading it tremendously. And it's a very short note. It was invited by the Siam Society on Applied Mathematics, and it's very short, but it gives you an insight on who von Kármán really was, and a true prodigy, a leader of leaders in aeronautics and astronautics. And in his study, in his technical note, actually, Dr. Sears wrote, "It was clear to those of us who worked close to him that mathematics, applied mathematics, was his true love." And because of that, we're going to see this idea recur throughout the presentation today. It was through his concepts that we were able to come up with some new findings, some new formulations that helped us uncover the physics in a variety of problems. Now, Bill Sears happened to be the advisor of my own major advisor. When I received my PhD, I studied under Dr. Bill Van Morum, who had studied at Cornell. So I've been fortunate to use in teaching aeroacoustics, perturbation methods, and aerodynamics and propulsion, those notes handed down to me through Dr. Sears from von Kármán himself. So I cannot tell you how excited I am to be talking about von Kármán himself. So again, he's known for a variety of concepts that he has developed. One of them is the von Kármán street, which refers to the alternating vortices shed from a cylinder in cross-flow. Of course, that problem, if you study its history, it's very interesting. It was given to Dr. Hemans, working with Dr. Prandtl, but Dr. Hemans could not understand why the flow remained unsteady. It was von Kármán who figured it out later on using his incredible mathematical skills. Of course, this phenomenon is named after him. Also, if you look at turbulence, and in the context of Prandtl's mixing length theory, we come across a constant kappa, which is equal to 0.4, known as the universal turbulent constant, or Kármán's constant, also named after him. And that applies to the overlap region, or the logarithmic log-law region that we teach in academia and also used in a variety of applications. Another well-known term that is used is the Karman line, that is approximately about 100 kilometers, which delineates the beginning of free space or outer space, so the edge of the atmosphere, that is also named after Dr. von Kármán. Now, however, of all the publications that Dr. von Kármán had, if we do a search on the Web of Science, by far his most widely cited publication is his work on the momentum integral approach. That was a 1921 paper. We on the board of the American Institute of Physics, and particularly the physics of fluids, had a special collection to commemorate that study a couple of years ago, and we received a number of contributions all the way from Ohio State University to Stanford, showing that this approach is still being used today. And of course, the approach itself, the momentum integral approach, is taught globally. You can find it in almost every textbook on fluid mechanics, both at the undergraduate and graduate level. I personally covered the entire theory last week at Auburn University in my Aero 3 course, which is on viscous aerodynamics. Every senior has to take that at Auburn. But to put it in context, we have to go back through time to 1904 with Ludwig Prandtl and his seminal paper. It was only an 8-page paper, yet many considered to be revolutionary in the sense that it laid out the framework for everything else to come. So up to that point, the analysis was limited to the far field, and through this paper, Dr. Prandtl was able to introduce the boundary layer equations that enable us to capture viscous effects, the skin friction coefficient, be able to predict separation, and so on. John Anderson wrote an article, a very short article in Physics Today. That's another recommended read to those interested in knowing more about Prandtl. Also, it was intended to commemorate that paper that he presented. It showed up in 2005 in Physics Today, and he refers to that paper as being revolutionary and being worthy of the Nobel Prize in aerodynamics. So 3 years after introducing the equations that govern boundary layers, Blasius, who was the first doctoral student working under Prandtl, was able to transform the Navier-Stokes equations into a simple two-term nonlinear third-order differential equation whose solution will give us all the results we are looking for flow over a flat plate. That solution by Blasius is still taught today. It's typically given as a project to the class to solve it numerically. The reason being it's highly nonlinear, it has a limited radius of convergence, and there have been many attempts to solve it analytically using the homotopy analysis method and other techniques leading to infinite series. However, we're going to talk about that later on today. It has been also used as a benchmark for both analytical results and in terms of testing new computational methods that seek to solve nonlinear problems. Now, let's talk about the 1921 paper, whose centennial we would like to celebrate today. It was published in the Journal of Applied Mathematics and Mechanics, ZAM. That was at the time one of the most prestigious journals in the world. That's where von Mises published the laws of stresses. And this paper really gave us a simple formulation for the shear stress connected to both capital U and little u. Capital U referred to the far field, and up to that point everyone knew how to capture the far field, and little u referred to the near field. That was the velocity profile within the thin viscous boundary layer that Prandtl had talked about a few years earlier. And it came as a response to the Blasius solution. The Blasius solution was fantastic. It's referred to as an exact numerical transformation or reduction of the Navier-Stokes equations, but it's limited to flow over a flat plate, whereas the momentum integral formulation by von Kármán applied to both laminar and turbulent flows, and truly could be extended to arbitrary configurations. So it had no limitations such as those applied to the Blasius model. And again, in order to solve it, one needs to know the far field, which was generally very well known, and also the near field, little u. And for that reason, Kármán's companion Paul Hausen, who had moved with him to TU Aachen, published a sequel. They were published back to back in ZAM, in which he provided polynomial approximations that helped us to capture and model the velocity profile within that thin viscous boundary layer. They varied from a first order, we are going to refer to them as KP1, KP2, KP3, KP4, from a first order polynomial to a fourth order polynomial. And F in this case is simply the normalized velocity. That's the little u over capital U, the fraction of the velocity within the boundary layer. And of course, eta in this case, that similarity variable is simply the fraction of the distance within the viscous boundary layer, delta being the thickness itself, what we call the disturbance thickness. And we're going to talk about those polynomials and also the paradox that they created and the reason why other methods came about later on. So if we have the momentum integral equation, it helps us obtain pretty much every boundary layer characteristic we're interested in finding, such as the disturbance thickness, the displacement thickness, momentum thickness, skin friction coefficient, we can predict the separation point, etc., etc. And it was so significant that, again, John Anderson wrote about it. Because of it, it helped give more attention to boundary layer theory within the community, which was very important to promote that theory. Next, I'm going to look at how it's usually presented in various textbooks. This is a table taken from Fox and McDonald's introduction to fluid mechanics, widely used. I did not want to use one from Frank Weitz's book that I helped co-author. But this is one, actually, when I was a student, I ended up studying through using this table. And you notice here on one hand, we have the different polynomials, first all the way to fourth order, and the different constants that we look for. Beta, for example, is the normalized momentum thickness. It's a very important parameter. It's a number that you can calculate for any given velocity profile. You can find beta. Also, we have a constant that we're going to refer to as A. This is really a constant that characterizes the boundary layer thickness. If we know A, we know the boundary layer thickness because there is a universal form for it, and that varies, of course. And there is another constant B, which gives us the skin friction coefficient. Now, there are many other parameters, but I want to limit my discussion to only two because we have a limited time to cover here today. And one thing that was noted as we moved from the second order to the fourth order, the discrepancy between those values that we obtain and those predicted by the exact solution, the supposedly most accurate solution named after Blasius, actually the error increased. To kind of show this more dramatically, I calculated the relative errors using any one of these polynomials, and let's take a look. So as we move from the second order polynomial to the fourth order polynomial, the error increases from about 3% to 13%, and most significantly in modeling the boundary layer thickness, the error using the supposedly most accurate polynomial, the fourth order polynomial, becomes of the order of 17%, which for many of us is considered to be unacceptable. As a result, many have abandoned the use of the momentum integral approach, the Kármán-Polhausen, and adopted other techniques such as Waltz and Thwaites that are also taught globally. This problem really bothered me for many years. I've been in academia teaching for perhaps more than 30 years, and I've asked every faculty I've come across who teaches the subject from MIT to Stanford why this happens, and the only answer I would get, hey, this is part of the beauty of aerodynamics and fluid mechanics. They are full of paradoxes. But it really bothered me that when we go to a higher order polynomial that is supposed to capture more correct boundary conditions, the ability of that polynomial to agree with the exact solution deteriorates. That did not make sense to me, so I decided to investigate this. And by the way, in order to find any one of these constants, A and B, for any given profile, one has to go through a set of algebraic operations, and these take a bit of time and effort. But throughout this type of effort, one can attempt to generalize. And the way I was able to reverse engineer this problem really happened while preparing for classes. I was able to come up with two constants, A and B. These are the same two constants we talked about, one being the boundary layer thickness, one being the skin friction coefficient, and find direct connections between the vorticity at the wall, which is also the slope of the polynomial, f naught prime beta, which is the momentum thickness normalized, and A and B. Those relations were so simple. If you multiply A and B, you get 2 f naught prime. If you divide B by A, you get beta. And then knowing how to connect the final answer all the way to the polynomial itself from its roots, it allowed me to to reverse engineer the problem, right, and essentially try to take a deep dive into it and understand why different polynomials do not agree with the exact predictions. And to kind of show this more clearly, I'm going to have some visuals. So this is a curve of the Blasius solution. The x-axis is the normalized velocity. So this is a velocity profile. So the x-axis is the normalized velocity, little u over capital U. The y-axis is the fraction of the distance within the boundary layer thickness. So 1 is at the edge of the boundary layer thickness, and 1 at the bottom will be the free stream, reaching the free stream velocity. And if we were to compare to it the KP2 solution, this is the quadratic equation proposed or postulated by Polhausen. It satisfies 3 boundary conditions: only no slip at the wall, free stream velocity equal to capital U, and 0 shear in the free shear layer. You get a profile that is more or less acceptable, but when you go to a third order, the error increases, and when you go to a fourth order, the error increases further. Again, let's look at this again. This is third order, this is second order. You go to third, the error increases, the disparity increases. You move to the fourth order, which is supposedly the most accurate profile, the error becomes substantial and visually very clear. And again, skipping forward several weeks of investigation, it turned out that this fifth compatibility condition that Polhausen postulated was unfortunately incompatible with the predictions from Blasius. So if you look at the exact behavior of the solution for flow over a flat plate, the curvature effect, which is the second order derivative right at the edge of the boundary layer at y equal delta, is not 0. Actually, it turns out to be of order unity. It's a large value that cannot be neglected. And by relaxing that condition, one can arrive at a far more accurate, simple polynomial that can replace the KP4 profile. And this is the polynomial that I was able to derive. Look at the substantial decrease in error by plugging it back into the Kármán momentum integral formulation, the error drops from 13% to about 1%, from 12 to 0.5%. And most importantly, look at the boundary layer prediction that used to be 17%. The reason many abandoned the use of the Kármán-Polhausen momentum integral approach, the error is reduced by 2 orders of magnitude. So in a nutshell, Kármán's momentum integral approach lives on, okay? It's still valid. We can continue to use it. And in fact, we've been coming up with new solutions for a variety of flow configurations that are unbelievably accurate. There's no need to go and use alternative ad hoc methods. The Thwaites method, by the way, is a very good method, but it's empirical. It's based on data fits. However, it gives no attention to the behavior of the solution within the thin viscous boundary layer. So we're very pleased with this solution. And those characteristics that I came across accidentally, I want to illustrate them visually here for you. A and B, for example, if you remember, if you multiply A and B, you get simply 2 F naught prime. And what is F naught? It's simply the coefficient of eta to the power 1, which is negative the vorticity at the wall. If you multiply A and B, you get simply 2 times F naught prime for every single profile ever proposed as a solution to this problem. And I tested it not only for those polynomials, for any other profile that's out there that's been proposed. There's the Lamb profile and many other profiles from UC Berkeley all the way to Stanford. So the other characteristic I mentioned, if you take beta times A, you get B, or B divided by A is equal to beta, the way I first came across that. And now let's look at also visuals. This is before. This is kind of the best model that was out there. And this is the after. You can easily tell that there's a significant agreement between the two. Now you could argue, and one question here from the audience would be, well, why is there a discrepancy at the top, right here at the corner? Well, that is not in our hands. That's because the Blasius model uses Prandtl's strict definition of the boundary layer edge, which is at 99% of capital U. If you remember, at y equal delta, little u is 99% of capital U, whereas Polhausen postulated little u equal capital U, and we tried to compare apples to apples, so we remained consistent with Polhausen's postulates through and through, except for the one compatibility condition that we discovered is incompatible actually with the solution, should be relaxed, and then the polynomials will continue to improve in accuracy. Now, we applied it to the modeling of a heated plate that's maintained at a constant wall temperature, and we were able to recover the exact coefficient of the Nusselt number within an error of less than 0.5%. All other models had errors exceeding 10%. So we're really happy about that. But we did not stop there. Having really discovered the tools to reverse engineer this problem, we went ahead and found a virtually exact analytical solution to the Blasius equation, which is taught numerically all over the world. Now we have a single solution. We don't need to solve that numerically anymore. We have a single expression shown here that is basically indiscernible from the Blasius solution. And it is not a curved fit. It is derived from first principles by applying the correct boundary conditions. So I'm really happy about that. And all the work that I've discussed here, if you want to get into the details of those, they are found in the 4th edition of Viscous Fluid Flow. So we also applied it to flow past a cylinder where there's a pressure gradient and variation. We also were able to get very good results for predicting the separation point and the skin friction coefficient. We got excellent results compared to numerical and experimental data. Now, again, the momentum integral approach lives on, but also it is empowering several other tools that are used worldwide today. One of them is FlyStream. This was introduced in 2012 by my colleague, Dr. Roy Hartfield at Auburn University, and his doctoral student, Dr. Vivek Ahuja. It's now really grown substantially. It is based on a surface vorticity solver. It's a panel code that uses surface meshes instead of volumetric meshes. It enables us to obtain quick results for aerodynamic measurements, including fluid surface interactions, flutter, flapping, morphing, etc., with very short turnaround times. It's very robust, it's high fidelity, it's perfect, it's ideally suited for early stages of design. When we are in the conceptual design phase, it's been mostly supported by NASA and the Air Force, and a couple of years ago, NASA featured it amongst the most promising new technologies that came out of their SBIR, STTR program. So this particular code, again being based on a surface vorticity solver, is primarily inviscid, irrotational, but the way it actually communicates with the viscosity at the surface is through the use of the momentum integral approach. So this is an example how the momentum integral approach is still empowering modern technologies in being able to capture viscous effects near the wall of any flight article. This is a extended version of the momentum integral formulation that is named after Standen. It takes into account the thermal variations within the thin viscous boundary layer. And recently, it's been extended to the internal flow dynamics in solid rocket motors, leading to an award-winning paper where it was shown to be able to capture the flow inside a solid rocket motor, in this case, the reusable solid rocket motor, very well, leading to very good agreement with experiments and other CFD codes. Okay, so the last segment of my talk will focus on cyclonic rocket engines. This has been my passion for the last 30 years, and this is one that my team takes great pride in. So just a bit about our team. We have been focusing mostly on advanced propulsion concepts, advanced configurations. Our goal is to improve the performance and the safety of large combustors such as thrusters, rockets, etc., by leveraging the beneficial effects of swirl dynamics and stable combustion. So our two areas of focus are rotating and injection-driven flows, especially cyclonic flows, and also acoustic instabilities and wave propagation. Our partnership with Orbitech back then, which is Sierra today, goes back to 95, 96. In 96, this is Bill Knuth, the chief engineer who came up with the first vortex engine concept, asked me to take over at the time and help in completing the proposal on the VIRA engine, the vortex injection hybrid rocket engine. This is an engine that was very neat. It was funded by NASA Marshall at the time, and we developed a model for it, was built, and it was fired. It led to a 7-fold increase in regression rates for hybrid rockets compared to the classical hybrids. Basically, it leveraged the motion of a cyclonic flow field inside a cylindrical grain. And we also looked after that at several cyclonic engine concepts, including the vortex combustion cold wall chamber, the Vision engine, and the VR35K, which is the flagship of Sierra today, the one capable of 35,000 pounds or 155 kilonewtons of thrust. All of those are cyclonic engines, and our team has carried out the bulk of computational and analytical studies that supported the developments of these engines. This is an example of the VCCW. I need to say a couple of few words about that. So the engine has tangential injectors at the bottom. Unlike any conventional liquid rocket engine, the injection of the oxidizer takes place at the bottom, just upstream of the nozzle, through several injectors. In this case, I'm showing 8. The oxidizer that boils off at a very low temperature, for example, oxygen boils off at 90 K, is injected tangentially to the inner circumference. It swirls around, travels up the chamber walls, and then at the top, it mixes with the fuel that is injected radially, combusts, and then courses its way out of the nozzle. Now, being at a low temperature, it acts as a film coolant. It creates a thermal barrier that protects the walls from the combustion products, thus preventing the combustion products from accessing the walls. So the reduced thermal loading is wonderful to have. The engine does not need cooling jackets. As a result, one can use a lighter weight engine, one that is shorter, more compact, and as we are going to see later on, it turns out to be also more stable than traditional engines by virtue of the swirling flow field in it. It's an engine that we've spent many years studying, and I have a lot of results to share with you. So this was sponsored by Dr. Marty Ciavrini, who's the current director of propulsion at Sierra Space. We've done the cold flow simulations. We've also carried out the reactive hot flow simulations for hydrogen, oxygen, propane, oxygen. We've done methane, oxygen, different combinations of propellants, hydrogen peroxide, and RP1. And you notice here that the temperatures are pretty high in the core region, yet the walls remain at a relatively low acceptable temperature, again, which reduces the thermal loading on the walls of that Vortex engine, making it very unique in performance. This is a top view and isometric view, just kind of more showing that we are able to demonstrate the proof of concept that the chamber is cool across the length of the chamber. And we also looked at various different configurations for injectors. We looked at co-swirling, counter-swirling. We looked at radial injectors, slanted injectors, axial injectors to try to eliminate those configurations leading to hotspots and those that actually are optimal. And in this process, we continue to analyze the problem. Now, the cooling effect, the fact that it's self-cooled, has been well established and celebrated in various magazines, including the December issue, the year-end review of Aerospace America, and Space-Time magazine, and many others. And imagine this picture here is one of my favorite. We were able to sustain hydrogen-oxygen combustion in a plexiglass chamber. Imagine that, right? Despite the very high temperatures and radiative effects, the plexiglass did not melt. This is really amazing. And of course, in 2012, the engine was built and tested on board a P-15 Garvey Prospector. It was flown in the Mojave Desert. It was using an ablatively cooled graphite nozzle that operated flawlessly, and the engine ran very stably. So let's take a listen. All right, so due to its flawless performance, Sierra Nevada at the time ended up buying out Orbitech. So all the engineers working for Orbitech ended up becoming Sierra Space engineers, and we continue to work with them. Now, the latest design of the Dream Chaser uses 20 Cyclonic RCS thrusters that leverage the different modes of combustion of hydrogen peroxide and RP1. And so this is the latest on the RCS thrusters that use the Vortex engine technology that we've been referring to. So on the other scale, we have the VR35K. This is the flagship of Sierra. It's a hydrogen oxygen Vortex engine. It's run using a fuel-rich staged combustion cycle, so it has a pre-burner, it's not power limited, and it's capable of very high pressures and therefore thrust. It's capable of about 155 kilonewtons of thrust while remaining compact and very stable. The advantage that it offers compared to other engines out there that use the expander cycle, it can allow for a much longer nozzle that provides for a larger expansion area within the same installation envelope. So it's a fantastic engine to consider, and it's very stable based on our studies. And there are many other also vortex engines that Sierra is developing for the lunar lander and so on. The RCS thrusters, as you saw in the video, are responsible for docking with the space station, for landing, for orbital maneuvering, and also for re-entry. And in our analysis, we do not only provide the full computational analysis, the CFD, to characterize the flow field within the engine. We also look at acoustic instability characteristics. We try to identify all the critical frequencies and stability acoustic signatures in any engine that we study. And what we discovered is that for the class of cyclonic engines, the higher the speed, the more stable they get, which is almost counterintuitive at first. But the best analogy I can give you is that of a top. When you spin a top, the higher the spin that you give to it, the more stable it's going to be. And this is our observation, and we're able to prove that mathematically, as did von Kármán back in the days with the von Kármán street. So the higher the injection speed, the tangential injection speed, the more axisymmetric the flow field gets, more coherent and more stable. I left the best for last. In our analytical studies of cyclonic engine, we started really with nothing. There was nothing out there to model the wall-bounded cyclonic flow, and yet we, using, again, von Kármán's ideas of space reduction and match asymptotic expansions, we were able to first come up with an exact solution for a flow inside a cylindrical chamber that was identical to the CFD results, uncovering the key characteristic parameters such as the vortex Reynolds number, the Ekman number, the modified swirl number, directly from the governing equations, and also following Kármán's lead of going from the specific to the general. We went from simple models to a general model that enabled us to capture any type of injection or outlet profile. And we uncovered a suite of very beautiful, elegant helical profiles that fall under the Beltramian, Terkalian, and complex lamellar classifications. And those enabled us, again, to uncover a set of fundamental characteristics that help us better understand the physics of the problem, the maximum tangential speed, the rotating forced vortex near the core of the chamber, which turns into solid body rotation. All of those parameters we were able to extract analytically. And one of the key characteristics when you talk about tornadoes or hurricanes or cyclones is something that is defined as the mantle. This is a rotating, non-translating cylindrical interface that separates the outer vortex or the updraft from the inner vortex or the downdraft. And we were able to locate that through our models theoretically. One was a cosine that led to a root of 0.707. One was a Bessel that led to a root of 0.628. And we were very pleasantly surprised to see that even at MIT, Joe L. Smith, who was the department head of mechanical engineering, who had a passion for hydrocyclones, had come across similar values for the root of, for the mental location in his hydrocyclones. And lastly, we moved from cylindrical configurations to conical cyclones and also to hemispherical cyclones, finding exact solutions to those problems and adding to our repertoire of engineering approximations that help uncover the physics of these very exciting novel problems. Before I close, one of the things we discovered through the analytical models is that along the length of a cyclonic chamber, there is leakage that is possible from the outer vortex to the inner vortex as a result of the cross-flow that exists along the mental location. And the longer the engine is, the larger the leakage will be. So the oxidizer that's being injected is going to short circuit and leave the chamber before it had the chance to combust. So we started moving towards better, more optimal designs that are shorter and ultimately landed on hemispherical configurations that do not allow any leakage to occur. Now, again, I cannot tell you about the most recent optimal design because it's highly proprietary, but just want to give you an idea of how the design evolved over time, inspired and guided by those theoretical results that we obtained. So in closing, I want to thank all of you for sticking around as we celebrate von Kármán and his momentum integral formulation, and also celebrate some of the findings we had, the breakthrough in understanding how the Paulhausen paradox can be resolved and coming up with actually solutions to it. And as a result, really the momentum integral approach that was introduced by von Kármán lives on today. We also, again, thanks to von Kármán's ideas that consist of systematic simplifications of the governing equations while retaining the gist of them, enabled us to extract absolutely beautiful solutions to a variety of complex, highly complex three-dimensional problems that helped us to shed light on a number of configurations related to cyclonic engines. So with that, I want to acknowledge some amazing individuals that I had the pleasure to work with, especially Dr. Kurt Polson, who nominated me for this award. I cannot thank him enough if I were to live 100 times. Also, many colleagues, my references, and Dr. George Lecieutre, who headed the selection committee, and every member of the selection committee. I cannot tell you how honored and humbled I am today to receive this award. And thank you very much.
Joe, thanks for such an illuminating lecture. I think that was a very fitting and great way to honor the centennial of one of von Kármán's major contributions and to demonstrate some applications in space propulsion.
Absolutely. Thank you so much.
The Institute's Honors and Awards Committee takes great pride in selecting accomplished leaders like Joe, accomplished leaders in aeronautics and astronautics who can share their knowledge through this von Kármán lecture. It's my great pleasure, on behalf of AIAA, to recognize you with the von Kármán Medal, the certificate.
Thank you so much. Thank you so much.
But wait, there's more. Congratulations. Right, we've got time for a few questions if you have any for Professor Majdalani. I know I do.
Sure.
Congratulations, Professor. This was very impressive and well-deserved.
Thank you.
My question is about the vorticity that's created by the injectors, whether there's a net torque on the whole rocket. And I noticed in the video that we saw of the launch that there was a significant rotation during the launch. Is that true, that there is a net torque generated? And could that be offset by a multi-engine configuration with opposing injection directions?
Yes, absolutely. Very good question. That was, in fact, a study that we performed to determine the torque. It's not as large as you might suspect, but it is there. As the the swirling flow field accelerates through the nozzle, the tangential component is transformed into an axial component predominantly. But as this conversion takes place, there is still a torque that is produced. And we're able to estimate that numerically and theoretically. As a result, you're absolutely correct. We typically design them with 4 of them side by side, especially for manned missions. And otherwise, there'll be, of course, controllers that will try to account for that torque during flight. Yes. Very good question.
Professor,
Sorry.
Congratulations. My question is there a difference between the startup sequence of these cyclonic engines and a regular liquid rocket engine?
I'm sorry, could you repeat the question? Is that
The startup sequence? So
sequence?
Like, is there?
How do you start the engine?
Yeah, how do you start? I guess how do you start the engine? That's a.
Oh, no, no, no. The starting, you mean they're all throttleable, right? The liquids are throttleable. Even the hybrid that I mentioned briefly is also throttleable. So you control, for the liquid, you can control both. Now, the RCS thrusters themselves can operate under three different modes. You can either use the hydrogen peroxide in a monopropellant mode. You take advantage of the decomposition, so it goes through a bed before it is injected into the combustion chamber or you can use it as a bipropellant with RP1, right? So you have three different modes, and those modes will lead to different thrust levels. For the RCS thrusters that are on board the Dream Chaser, there are 20 of them, and they have thrusts of, I believe, 40 pound force, about 60 pound force, and the highest, when you use it in a bipropellant mode, which is capable of the most thrust level, you get about 110 pound force. But the operation is identical to that of a traditional rocket engine. Yes. Any other questions?
I'll take a question.
Okay, sure.
And I'll start with an observation. Just in case there's anyone out there who doubts or needs additional evidence regarding the essential unity of aero and astro in aerospace, I point out that in addition to today's von Kármán lecture in astronautics,
Yes.
which had to do with fluid mechanics and applications to space propulsion, this year's Wright brothers lecture in aeronautics was on the topic of the Mars helicopter. Nice. So I kind of like that. So you mentioned that von Kármán's real love, or one of them, was applied math.
That's correct.
And that he loved nothing better than to, I'll say, successfully distill some complex physics down to a relatively simple differential equation type model.
That's correct.
The PDE. And I guess success in that context means that it's a model that reproduces experimentally observed behavior and quantified results.
Yes.
I noticed there were some, let's say, younger theoreticians in the audience, maybe. I wonder if you would have any advice for them regarding the importance of experiments and teaming up with other people who can help you stretch your own abilities. I guess this is kind of a softball, but
sure. Well, absolutely.
I'm sure you'd have something to say about it. That's why I wanted to ask.
Well, first off, I would encourage every experimentalist to, and it goes both ways. So every experimentalist, I would encourage them to study asymptotic theory. That was von Kármán's passion. And through asymptotic or approximation theory, you can find solutions to complex problems to which you could then compare your experimental results to. It will help you in publications. Any journal would love to see experimental data that's corroborated by theory, or vice versa. Any theory is not complete without some experimental evidence. And for those of us who are theoreticians, I consider myself to be mainly a theoretical person. I love to use analytical and computational models. Also, we are badly in need of experimental data, and we also encourage those from the government and industry to share with us more easily some of the data, because some of the data on rocket engines is very difficult to obtain. A lot of times we carry out our studies in a double-blind kind of manner. We provide the results, but we do not see what the other person has because of the proprietary nature of most rocket engines. That essentially the data is retained by the sponsor themselves. So that would be my recommendation, is to cross-pollinate and kind of always seek to broaden your horizons. If you're an experimentalist, to also seek to develop strength in analytical modeling and vice versa.
I am hopefully one of those future theorists, and in fact, I'm taking an asymptotic approximation class right now, which seems perfect for me.
Outstanding.
My question was, when you look at something as complex as like a vortex engine, as you're discussing, is there opportunities to try to analytically and asymptotically find like models describing that, or do you mostly use computation for that? And if you can do analytically, like how do you develop a model? Like what's the process there?
Very good question. When we started looking at wall-bounded cyclonic chambers, there was literally nothing out there. The only models that existed, such as the Rankine, Oseen-Lamb, Burgers-Rott, Sullivan, were one-dimensional models that did not even have more than one component of velocity. So when we look at this cyclonic engine, the first thing you notice, it has 3 components of velocity. The only thing we could do is make the assumption that it's axisymmetrical, which is actually well justified. The axisymmetric assumption is, so you end up solving it as a 2-dimensional problem if you want to look at a steady state condition, or 2-dimensional time dependent. So that simplifies it a bit. Then I could spend with you the entire week about what kind of models are most suitable for these types of flows. The Bragg-Hawthorne equation is, we discovered after much digging, one of the most amazing frameworks out there. The Bragg-Hawthorne equation is essentially Euler's equation, but simplified to a form that is directly applicable to swirling flows. So if you have a swirling flow field, instead of going and trying to solve the full Navier-Stokes equations in their full glory, you can simplify it to a Bragg-Hawthorne form, and that Bragg-Hawthorne form allows you to extract those really neat solutions. Now, to answer also the other part of your question, we have, for all of those models that I showed you, we have obtained not 1 or 2, but more than 3 exact solutions to the same problem under different conditions, and then we augmented them with asymptotics, right, using perturbation theory that you are studying, to capture the viscous boundary layers or the thermal boundary layers. These are always tricky to obtain exactly, right, without solving the equations from ground up. You solve them asymptotically, again, a la von Kármán, or following Prandtl's idea. Remember, Prandtl and that 1904 paper I talked about earlier is the one that revolutionized aerodynamics. He is truly the grandfather of aerodynamics, Prandtl and his team. You know, you have Prandtl-Meyer, Prandtl-Glauert expansions, and then von Kármán came and really took it to the next level, and is sort of the father of modern aerodynamics and astronautics as well, because he focused also on rocketry, he was not just focusing on aeronautics. But Dr. Lesieur said something really important here. It's the coming together of both fields. We could not have made those milestone achievements and improvements in modeling the vortex, the class of vortex engines, were it not for the information we were getting from the aerodynamics, right, and the fluid dynamics that helped us improve the design, eliminate hotspots, eliminate the leakage, and come up with a robust, highly stable engine. And again, all thanks to the good men and women that have been working on this and developing those engines experimentally.
And I think that's an excellent place to wrap things up.
Sure.
So let us all congratulate and thank Professor Majdalani once again.